Hi, my name is Gerard Lemson. I'm at Johns Hopkins University, previously at the Max Planck Institute for Astrophysics. This is a map of the universe as constructed by the Sloan Digital Sky Survey. Every point you see is a galaxy, something like one of the things on the right bottom. Surveys like this have revolutionized astronomy, and much bigger ones like LSST are coming around. One of the really revolutionary things that SDSS did was to actually publish all the data that they had behind an interface that ultimately actually even allowed people to just write custom SQL queries. So astronomers have been able to start using this kind of like a virtual telescope or writing SQL. This very complex structure requires that for understanding it, we need complex models as well. And complex models like this can these days only be created using simulations. The Virgo Consortium, which Johns Hopkins is now also part of, has run lots of these simulations. On the background, you see something like this, which is the now well-known Millennium Run simulation. You see the same kind of frothy structure that we saw in the actual distribution of galaxies on the sky. You see very dense points, clusters, which is where we think galaxies form. In fact, the Virgo Consortium tried an experiment and started building a similar kind of database as SDSS. And so what we did is we concentrated actually on these kind of dense clumps, except that, of course, using cluster extraction that was running in situ during the simulation, every clump is just a single point with some properties, except that here, because we have time evolution, you see a very complex merging history. These merger trees are the basis for other algorithms, and here on the left side you see little red and blue points that represent galaxies, so with maybe hundreds of properties. They don't really look like the galaxies that you saw earlier, though. I mean, they have lots of the proper scaling relations and all of that on statistics. They also have here merger trees, but at some point we want to go into more details of the simulation. With the kind of simulation that we have, this means that we have to go down to points. This is an example of our simulation, by the way, sorry. So the simulations that we ran are so-called dark matter-only simulations. So you have initial conditions plus gravity, that's all of the physics. But you see already that these clumps actually have structures that are not very spherical. What we want to do is to allow people to get actually access to the raw data. This is the core of the part. The simulation data can be very large. We have simulations from 10 to 300 billion particles per snapshot, of which there are hundreds, 300 gigabytes to 9 terabytes. This is expensive for us. We don't have a lot of money. So we come up with we cannot load the data in the database. It would at least double the storage size. It would present bottlenecks, etc. It would take a long time. So we come up with something that for now we coined FileDB, that we don't ingest data in the relational database. We leave it as files, accessible from within the database. We need to try to avoid scans. And here we can use the fact that that the files, the raw data files, are organized according to a space filling curve. Every file contains a certain block. There's order of 512 files per snapshot. Every file contains a block of the space filling curve. We index the files by the block that they contain in the database. Within each file, the particles, are also organized spatially. So what we now can do is when you want to find the particles in the sphere, for example, we first calculate the cells, 256 cubed cells that we distribute this space-filling curve over. We can calculate in the database what cells are interactive. We can index it now. So what this now means is that we have, say, a couple of ranges in this index curve, and we can actually go into the database, find out which files contain at what offset the cells and how many particles there are. So this we can all do in a database by extending it. We have a SQL Server database, which with C# code allows us to extend this rather elegantly. So we can write simple table-valued functions, like here, something called Millennium Particles that finds all the particles in the sphere. We can now join it using cross-apply to the main data in the halos, the dark matter halos. We can make it even more complex, so we calculate density profiles, all in SQL by accessing the files. And we even now have a system where you don't have to bring any data back anymore if you want. We can actually run Jupyter notebooks inside of Docker containers on the server side that talk to the data, you get the density profile, You can fit them directly to some model curves, and you don't have to do you can do everything remotely, which we call size over compute. Thank you.